Ever wonder how AI systems learn to make smart choices without getting stuck in a loop? Like, how does a robot figure out the best way to navigate a warehouse? Or how does a game AI master a level without repeating the same mistakes? It all comes down to a clever trick called reinforcement learning, where machines learn by trial and error, like a kid figuring out how to ride a bike. But here's the big question. How do we know if an AI is actually getting better? Enter Markov Decision Processes, a framework for modeling decisions in uncertain environments. Think of it like a game where you don't know the rules up front, but you keep playing to figure them out. The goal? To minimize regret, the difference between the rewards you could have earned with perfect knowledge and the rewards you actually get. It's like playing a board game where you're constantly adjusting your strategy based on what you learn along the way. Now, here's the twist. Researchers have cracked a code for a specific type of MDP called communicating MDPs, environments where every decision eventually leads to every other decision, like a maze where no room is ever truly isolated. In these scenarios, they developed an algorithm that asymptotically optimizes regret, which means it gets better and better over time, approaching the best possible performance. Imagine you're solving a puzzle, and there's a hidden difficulty level that changes as you go. The algorithm uses a value called K(m) to gauge how tricky the puzzle is. The higher K(m), the more complex the environment. But here's the catch. K(m) isn't smooth. It can jump around like a bumpy road that throws off your GPS. To fix this, the researchers added a regularization mechanism, a clever way to smooth out those jumps and estimate K(m) accurately from data. This isn't just theory. Previous methods either made strict assumptions about the environment, like it being ergodic, meaning it forgets its past, or couldn't guarantee top performance. This new approach breaks through those limits, proving that in communicating MDPs, you can always minimize regret as efficiently as possible. Picture a robot learning to navigate a warehouse. With this algorithm, it explores smarter, avoids dead ends faster, and adapts to new obstacles without getting stuck. It's not just about solving a maze. It's about building AI that's resilient and adaptive in the real world. So next time you see an AI making decisions, remember, behind the scenes, it's battling the same challenge we've discussed today: how to learn optimally in an uncertain world. And thanks to research like this, the answer is getting better every day. Thanks for watching. If you enjoyed this deep dive, hit subscribe for more explorations into the fascinating world of AI and machine learning. Until next time, keep learning. Hey there. Ever wonder how AI systems figure out the best way to do something? Like a robot learning to navigate a maze, or a game-playing algorithm mastering a new level. It's not just luck, it's math. Today, we're unpacking a key insight from a research paper that shows how these systems learn to explore efficiently, and why that matters for the future of smart technology. Let's start with a simple question. How do you know an AI isn't just guessing? Well, researchers use something called a co-exploration structure to prove that, over time, the AI's behavior becomes predictable and optimal. Think of it like a chef perfecting a recipe. At first, they taste and adjust, but eventually each bite is consistent. No more random experiments. This is what Lemma C13 shows. After a trigger event like the chef tasting the dish, the robot's exploration of the maze starts matching an ideal pattern. But how do they prove this? The answer lies in breaking the AI's journey into exploration epochs, like chapters in a book. Each chapter has its own rules for trying new paths, and the math ensures that, over time, these rules lead to near-perfect performance. Even if the robot takes a wrong turn now and then, those tiny mistakes get averaged out thanks to clever statistical bounds. It's like saying, sure, you might spill a little sauce while cooking, but overall the dish turns out great. So what's the big deal? This isn't just theoretical. It means that, given enough time, the AI stops fumbling around and starts working like a pro. The initial burn-in phase is just the learning curve. After that, the system becomes reliable. Imagine a self-driving car. At first, it's cautious, testing every turn, but eventually it drives smoothly, making split-second decisions with confidence. This research is a stepping stone for real-world AI. It shows how algorithms can balance exploration and efficiency, avoiding costly mistakes while adapting to complex environments. Next time, we'll see how this applies to actual algorithms and why it's a game-changer for machine learning. Stay curious, because the future of AI is all about learning smarter, not just harder.